Okay, vaporization. So here we have an illustration of a beaker of water. The beaker's not covered. And what's going to happen is that gradually the water will evaporate, right? From our life experience, we know that if you leave a container of water sitting out open to the air and wait long enough, it may take weeks, all that water will just disappear, right? It will evaporate. These molecules are in constant motion. They have an average molecular energy. That means that some of them have higher molecular energy and some of them have lower molecular energy or thermal energy. And so if you have one that is moving quickly and it gets near the surface, it may have enough energy to break away from the intermolecular forces that are holding it together, and it can escape into the gas state. That's called vaporization, going from a liquid to a gas. If you've got a water molecule in the gas state that, gas molecules travel in straight lines till they run into something. Well, this guy's headed straight down. He's going to crash into the surface of the water, and he's going to get stuck. Going from a gas to a liquid is called condensation. This is a nice quote from Roald Hoffman. It's a wild dance floor there at the molecular level. So this isn't animated, but I imagine all of these little water molecules. This is like a mosh pit or something, These guys are dancing. They're grooving. And just like with people dancing, some people dance kind of slow, and some people dance real wild and crazy, right? So that's what's going on here. So average energy. So here, if we look at the fraction of molecules versus kinetic energy, at a given temperature, we're going to have some sort of a bell curve. So we've got an average thermal energy, an average kinetic energy, but some are very high in energy, and a few are very low in energy. If we increase the temperature, we increase the average kinetic energy of the molecules, and this curve also starts to spread out. What we've done here on the graph is drawn a dotted line here to represent the minimum kinetic energy needed to escape. Okay, so there's some minimum amount of energy needed to escape, and shaded here are the particles that are at that or above. Those can escape if they get to the surface. My favorite analogy for vaporization is the childhood game called Red Rover. Did you guys ever play Red Rover? They don't let them do that in school anymore. They can't even play tag. It's like somebody might get hurt. Yeah, somebody might die of an aneurysm sitting on the bench too. Anyway, Red Rover, if you're not familiar, you get two groups of children out on the playground, and they hold hands, making a line on each side facing each other. So you get these two Red Rover lines, and then they say, Red Rover, send Sally right over. And Sally from across the field comes running as fast as she can at the line, and she's trying to break through your hands. You're holding on, and she's trying to break through. You can see why people could get hurt. Sure, broken wrists, a good way to break a wrist. Anyway, the faster she runs, the more likely she is to break through. But it also depends on how strong are the people that are holding hands. If she's been at the school for a while, she maybe knows that this little girl over here is pretty wimpy. So she's going to run where she is instead of where those big, tough boys are, right? Okay, so intermolecular forces, the strength of intermolecular forces, how strong are the people holding hands in the Red Rover line? The kinetic energy is how fast and how big is the person running. So if you think of kindergartners playing Red Rover, or maybe the linemen from the Fresno City football team playing Red Rover, it's going to be a rather different game, isn't it? If you get a lineman running at a kindergarten lineup, he's just going to go right through. He doesn't even really need to be moving that fast, right? Remember, kinetic energy is mass times velocity squared, 1/2, right? So how big it is and how fast it's moving. So at a lower temperature, there are fewer particles that have enough energy to break through. At a higher temperature, this is those same people running faster, they're more likely to get through. So at high temperatures, vaporization occurs more quickly. We know that from experience, right? Think of maybe a wet towel. Well, if it's sitting in the trunk of your car, or if it's spread out on the hot driveway, where's it going to get dry faster? On the driveway where it's warm, right? We heat things up to dry them because it speeds up the rate of evaporation. I don't want to talk about that one just yet, but liquids with stronger intermolecular forces evaporate more slowly. So you got the O-line guys in the Red Rover line. They have powerful grips. You're going to have to be moving awfully fast to break through there, right? You're going to have to get to a much higher temperature before significant evaporation will occur. So if you have strong intermolecular forces, you have a lower rate of evaporation. And this brings up two terms that we've encountered before, at least this one, volatile and non-volatile. A volatile liquid vaporizes easily. A non-volatile liquid does not vaporize easily. So which is going to have stronger intermolecular forces, a volatile liquid or a non-volatile? Non-volatile. Those molecules are holding on to each other more strongly. It's hard for molecules to escape through that line. Another way to increase the rate of vaporization, besides increasing the temperature, is to increase the surface area. So at the surface, the molecules are held less tightly. And also, in order to escape, a molecule has to get to the surface. So if you make the surface bigger, you have more opportunities for molecules to escape. So if you think about it, a cup of water, maybe you have two identical cups of water, and you spill one on the floor and you leave one on the counter. Which is going to evaporate faster? The one on the floor, right? Because it has more surface area. What about the energy involved with things evaporating? So we had that beaker sitting on the counter. If the beaker is thermally insulated, so it can't take in energy from the surroundings, what's going to happen to the temperature of the water as it evaporates? What molecules are leaving as they evaporate? The high energy ones or the low energy ones? The high energy ones. So if it's only the highest energy molecules escaping, what does that do to the average kinetic energy of what's left behind? It goes down. So the temperature will decrease. Temperature is a measure of average kinetic energy. Vaporization is an endothermic process. So with a beaker sitting on the counter, you're probably not going to be able to measure a temperature difference, because as those high energy molecules escape and lower the average kinetic energy, you have thermal energy coming in from the surroundings and replacing it. Here's a guy running, getting sweaty. Why do we sweat? To cool us, right? You get sweaty and you step in front of a fan and it's like, oh, that feels so nice and cool, right? It's because it's causing the sweat to evaporate faster. As sweat evaporates, it's the warmer molecules, the higher energy molecules that leave. They're taking energy from your skin, and so they cool you down. So sweating is a good thing to cool you off. Personally, I'd prefer to just avoid sweating, but around here, that's not possible. So vaporization and condensation are opposites of each other, right? So if evaporation is endothermic, then condensation must be exothermic. Condensation is exothermic. Have you ever opened a bag of popcorn and got your hand in front of the steam? Man, that hurts, right? Steam can burn you very, very easily. What's going on there? The gas molecules have high energy. When they condense, they release energy. Where does the energy go? Into your skin. Just like sweat evaporating takes energy out of your skin condensation releases energy, and that can cause a serious burn. This condensation, being an exothermic process, has a big effect on climate. So I pulled up some numbers. These are average daily temperatures in July, averaged from 1971 to 2000 for Fresno and San Francisco. Average high in Fresno, 96.6, sounds about right, maybe even a little low. But this includes nighttime, okay? Yeah, 96.6. And in San Francisco, 68.2. I lived in Foster City, which is very near San Francisco, and I swear it's almost colder there in the summer than it is in the winter. It's really strange. Then let's look at the low, the average low. I'm sorry, that's the average high. I don't know what I'm saying. Average high, average low, 96, 66. The difference is 30.5. In San Francisco, the difference is 13.8. The temperature does not fluctuate from the high of the day to the low of the day very much at all. Here, it can fluctuate wildly. That's the average difference. Some days we have 40-degree difference, right? It's 100 in the afternoon, and it's 60 at night. And that's why we're so messed up. You just don't even know how to dress. So you just dress however you feel, because at some point in the day, you'll be dressed appropriately, right? You just have to wait for that time and suffer until then. So why? Why is Fresno like that? Why is San Francisco like that? San Francisco is surrounded by water. Sun beats down during the day. The water absorbs it. There's evaporation occurring. It absorbs the energy. Nighttime comes, the energy from the sun is gone, and now the water starts, the water in the gas state starts to condense and releases energy. And so vaporization and condensation moderate the temperatures. In Fresno, it's very, very dry, and so there's very little moderation of the temperature, and so we get these big temperature fluctuations. And you go someplace like the high desert, where it's even drier, and you get even bigger temperature variations. Well, there's energy involved, so of course we have to think about how much energy. So what we call the heat of vaporization, or enthalpy of vaporization, we represent this as delta H vap, because we're talking about a change in enthalpy. This is the amount of heat needed to vaporize 1 mole of liquid at its normal boiling point. So for water, 1 mole of water from the liquid to the gas state requires that you put in 40.7 kilojoules of energy. So heat of vaporization is always a positive number because it's always an endothermic process. It depends on temperature a little bit, but not a whole bunch. So here we have some different liquids: water, isopropyl alcohol, acetone, dimethyl ether. Here are their normal boiling points, and here are heat of vaporization at the boiling point and at room temperature. So water has the highest boiling point. That has the highest or strongest intermolecular forces. Rubbing alcohol is up there as well. It also has hydrogen bonding. Acetone and dimethyl ether. Dimethyl ether is much less polar. And we see that with these lower boiling points and weaker intermolecular forces, that the heat of vaporization is also lower. There's a small difference between at 100 and at 25, but it's not a whole lot. When a substance condenses, the same amount of heat is involved. It's just the opposite direction. So you've got gas condensing to a liquid. You take that heat of vaporization and you put a negative sign in front of it. So you condense 1 mole of water, it releases 40.7 kilojoules of energy. It has to be the same, because otherwise you could create or destroy energy just by vaporizing and condensing something. You can mess around with that, but you're not going to make energy that way. You can't. This heat of vaporization is a conversion factor between amount of heat involved and the number of moles of substance. So we can do an example like this. Calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. But we need a number here. We need a heat of vaporization. So let's go back and look at the table. This is at its boiling point. So for water, heat of vaporization, 40.7 kilojoules per mole. So delta H vap equals 40.7 kilojoules per mole. So we can approach this as a unit conversion problem. Here we've got kilograms of water. We want heat in kilojoules. So our path here is kilograms. We want to end up with kilojoules. This is a relationship between kilojoules and moles. Right? So we need to get moles in here. And how do we get from kilograms to moles? We need the molar mass. Molar mass is usually grams to moles, so we need to go to grams. .58 kilograms of water. I want to convert this to grams of water, and then to moles of water, and then to kilojoules. And here is dimensional analysis coming back yet again. Kilo means 10 to the 3. Some of you are still having a little bit of trouble converting kilo and milli. Kilo means 10 to the 3, so I'm going to put what it means on the opposite side of the line. 1 times 10 to the 3rd grams is 1 kilogram. Alternatively, you could write 2.58, and instead of writing kilogram, you could write what kilo means. 2.58 times 10 to the 3 grams, because this part is the K. Molar mass, 1 mole of water, 18.02. And then here's our conversion factor, the heat of vaporization, 40.7 kilojoules per mole. So calculator says 5827.19 kilojoules. There's some other digits too. How many sig figs? 3. Our mass had 3, and our heat of vaporization has 3. So you could round this to 5830. Some of you do that really well. You cannot round this to 583. Okay, some of you do that very well too, but it's wrong. So 5.83 times 10 to the, right? So, what am I doing? Having issues, that's what I'm doing. Moving the decimal point 1, 2, 3 places. So this is 5.83 times 10 to the 3rd kilojoules. Any questions?
Are you going to give us the 40.7?
You will be given the heat of vaporization either in a problem, it might actually be included in the question, or in a table to refer to. Yeah, you don't need to memorize those. Any other questions? Now we're going to look at vaporization in a closed container. So here we have an Erlenmeyer flask with a stopper. There's water in the bottom. Originally, there's essentially no water in the air above it. And what happens? Well, the water begins to evaporate. As the water begins to evaporate, now we've got water in the gas state inside this flask. And those molecules do what all gas molecules do. They go in straight lines till they run into something, and then they bounce off. And they just keep going like that. And eventually some of them are going to hit the surface and get stuck. That's condensation. So we have evaporation occurring and condensation occurring. Initially, we only have evaporation because there's nothing to condense yet. As more evaporation occurs, we get more gas molecules, the rate of condensation increases. Eventually, we get to a point where the rate of evaporation is equal to the rate of condensation. That's called a dynamic equilibrium. It's dynamic because condensation and vaporization are still going on. Molecules are leaving, molecules are coming back, but they're doing so at the same rate. And so overall, the amount of water in the gas state and the liquid state is constant, but it's different molecules. It's like people at an airport. There's people coming in on flights and people leaving on flights. So maybe overall, the number of people in the airport is roughly the same, but it's not the same people all day long. So the rate of evaporation is going to depend on temperature and surface area, but those are constant here. The surface area isn't changing, the temperature's not changing. The rate of condensation is going to depend on the concentration or pressure of the gas. That's going to increase as more vaporization occurs and then level out. So we can look at a graph of this. At time 0, we have no condensation because there's nothing to condense. But we have evaporation. The rate of evaporation is going to stay the same over time because the things that affect vaporization aren't changing. Temperature, surface area, intermolecular forces, it's water all the time, so none of those things are changing. The rate of condensation depends on how many gas particles are in that space. And so as evaporation occurs, the rate of condensation increases. And it will increase to a point until they're equal. So that gas concentration is called the vapor pressure. It's the partial pressure of whatever that liquid is. That vapor pressure is going to depend on the strength of the intermolecular forces. So if you have weak intermolecular forces, you're going to have more gas molecules than if you have strong intermolecular forces. Because at a given temperature, if you compared something like water and something like acetone, acetone has weaker intermolecular forces. At the same temperature, the rate of evaporation for the acetone is going to be much higher. Any questions about that?
So eventually it balances?
Yeah, eventually it balances. Because as the rate of evaporation, as evaporation goes on, the rate increases in the gas state. And so the rate of condensation increases. But then you get to this point where the rate of evaporation is finite. It's fixed, it's the same. And so you're going to get to a point where the partial pressure, the concentration of the gas, is no longer increasing. Because as soon as it starts to go up, it condenses, and so it just stays the same.
Is that why we always use water but not water vapor in those containers?
You don't see the water vapor because the individual molecules are too small to see. So you can see the liquid, but you can't see the gas. It's there, though. There's water in the air right now.
So just to clarify, is this happening though only in sealed containers?
You're only going to get this equilibrium in a sealed container. Because if the container is open, most of those gas molecules are going to leave, right? They're just, if one goes straight up, I mean, it could go straight up till it hits the ceiling or whatever, and it's not going to happen to bounce back. Good point. So here we have a container that has a piston in it so we can change the volume. So here we have, I think this is pentane. So here we have liquid pentane, and we have evaporation occurring, and we have condensation occurring. If we leave this for a few minutes, we'll get a dynamic equilibrium where the rate of evaporation and the rate of condensation is equal. And so the amount of gas is the same. It's constant. So that would be the partial pressure, the vapor pressure. If we expand the volume, of the container, what does that do to the concentration of the gas? It decreases it. Now you have the same number of particles spread out in a larger area. That is a lower concentration, a lower pressure. So then what happens is the rate of condensation decreases. Rate of evaporation stays the same. And so in that curve, you're just going to, never mind, I don't want to talk about that. Anyway, so the rate of evaporation stays the same, rate of condensation goes down, and so more of this will end up in the gas state until we end up with the same concentration. So it doesn't matter how big the container is or how small. The partial pressure of that gas, the vapor pressure, is going to be the same if it is in equilibrium with its liquid. It's always the same. If we take this now and we make the container smaller, decrease the volume of the gas, that increases the concentration of gas. If you think of number of gas particles in a particular volume, that's going to increase the rate of condensation, and so more gas particles are going to condense, and they're going to keep doing that until they get back to dynamic equilibrium. This is called Le Chatelier's principle, where if you have a system in dynamic equilibrium and you mess with it, you disturb it, it is going to change in a way to minimize what you did to it. So we increased the volume, which decreased the gas pressure. It's going to change in a way to bring that back up. And equilibrium is a lot like me. I don't like change. I will fight you if you try to change things in my life. Change is only good if it's my idea. Any questions? Vapor pressure is going to depend on temperature. Here's water, this reddish line. And this is vapor pressure measured in torr. So if we take water down here and we start to heat it up, think about what's happening to the molecules. The average kinetic energy does what as you increase the temperature? It increases. And so you're increasing the number of water molecules that have enough energy to evaporate. So you increase the rate of evaporation. Higher temperature, higher rate of evaporation. Well, what does that do to the vapor pressure, the pressure of the gas above it, if you're increasing the evaporation? It's going to increase the rate or increase the vapor pressure. So as you increase the temperature, the vapor pressure increases. When you get to 100 degrees Celsius, the vapor pressure is equal to atmospheric pressure. And that's when boiling occurs. We can see for ethanol, there's a similar curve. For diethyl ether, as you increase the temperature, the vapor pressure increases. And so a small change in temperature can give you a large change in vapor pressure. This is why when we talked about Dalton's law of partial pressures and collecting a gas over water, we were concerned with what's the temperature here. It's because the temperature determines how much water is in the gas state, determines the vapor pressure. And so if we want to look at the other gas, we need to be able to subtract the pressure from the water. We need to subtract the vapor pressure of water from the total pressure to get the pressure of the gas we're interested in. Here's ethylene glycol. This is often used as an antifreeze. This has a very low vapor pressure. It does not evaporate well at all, which means it has a really high boiling point too. So the boiling point is the temperature at which the liquid's vapor pressure is equal to the external pressure. When water is boiling, what's happening is that molecules on the interior of the liquid have enough energy to break loose. When they were just evaporating from the surface, remember the forces of attraction at the surface are lower. But now these molecules have enough energy to break loose from each other even in the interior of the liquid. And so they'll form these bubbles of gas. And of course, these are much less dense than the water, so they'll quickly rise to the surface and pop. But here the vapor pressure is equal to the atmospheric pressure. So we sometimes refer to the normal boiling point of a liquid. That's the temperature that it boils at 1 atmosphere of pressure. Because if we change atmospheric pressure, that affects the boiling point. Let's go back to this picture. So water boils at 100, ethyl alcohol at 78.3, diethyl ether at 34.6 degrees. Well, what if we had only 600 torr of pressure above this liquid? Well, then water would boil at about, I don't know, about 90 degrees. It would boil at a lower temperature. This is a very important concept that is not always obvious to people. So here's temperature as we're adding heat. So you take some water and you add heat to it, the temperature goes up. Okay, we're familiar with that. The temperature goes up, goes up, goes up. The water starts to boil. Now, I think most people would say, if you keep heating the boiling water, it's just going to get hotter and hotter, right? But it doesn't. You get up here to the boiling point, and you can add more heat, the temperature will not change. It's going to stay at that temperature. Any extra energy you're putting in there just goes to more rapid boiling. It does not increase the temperature. So, if you're cooking spaghetti or something, just go ahead and throw it in there as soon as the water starts to boil. It's not going to get any hotter. It's just going to stay that temperature. So as long as you have liquid water present, the temperature will not go above 100. As soon as the last water has evaporated, then the temperature will shoot up. Your pan will start to smoke and burn, and your mom will get mad. So any questions about that?
So there's no way to get it still hotter?
That's a good question. Is there any way to get the water to boil at a hotter temperature? You heard of pressure cookers? Why do people use pressure cookers? They cook your food faster. How do they do that? Well, if you put pressure here, the boiling point is higher. So we go back to this graph. So if we increase the pressure, then the boiling point goes higher. And so you can cook the food faster because it's boiling at a higher temperature. That's why frying cooks things faster, is because you can heat oil above 100 degrees Celsius. You can't heat water above 100 degrees Celsius at normal atmospheric pressure. There's another picture in here. I want to, what? I don't know where it went. Oh, I remember. I didn't put it in there. Oh, well. There's a table in your book that shows boiling points of water at different locations. So I don't know if you ever bake, you look at the directions on the box of the cake mix, and it has high altitude directions. Well, at high altitudes, water boils at more like 94 degrees Celsius, and so then you have to adjust the cooking time or the cooking temperature or something, because it's not going to come out the same. Okay. Steam will get hotter, yeah. Yeah. And steam burns much more effectively than water does. Okay, so here's this relationship between vapor pressure and temperature. It's not linear. We like linear equations, linear relationships. I'm looking at the clock, and I'm looking at this, and I don't want to start this now, so we're going to stop. We'll deal with this next. After spring break, that sounds good.